same. Now I show you. See, the N is attracted. If I return this and face the S, it's going to repel. See, it's repelling. This is another experiment I did. You can tell this is a wire, thick wire, and then I mark north all the way, and the opposite side I marked south. But you can tell the first one is clockwise, second one is counterclockwise, again clockwise, counterclockwise. But what happened here, if I connect this to 12 volt DC, you can tell even though the flow of current is not changing, but due to the change in their orientation, one will show south, north, south, north. I'll demonstrate in a minute. You can tell the first one is south, second one is north, again south, north. But again, this has to do with the electric dipole moment orientation. That has to do with the orientation of the dipole or the position of charges. It does not indicate the direction of the field originating in these charges. When I make the loop from clockwise to counterclockwise, the dipole's magnetic moment orientation is reversed, but the flow of electrons is not reversed. This is another example. It's the same thing, clockwise, counterclockwise, but we can tell the flow of current or flow of electrons are not changing. It's the orientation which is changing. This is another experiment. In fact, Michael Faraday and Andre Ampere both discovered when we have more windings, well, of course not like this, they must be tied and close together, more winding in the same direction, the total magnetism will add up. But like I said, there was no logical explanation why, so I just demonstrated in an easy way so we can comprehend exactly why the total magnetism. See, this is just like a cross section of one winding. Well, of course you can tell 1, 2, 3, 4, 5. Technically this is a 5 layers winding, but you can tell always the one side is south. It doesn't matter all the way, but see, south is facing north, north is facing south all the way. As long as the direction, as long as the winding is in one direction, like the other experiment is not one clockwise and not the other one counterclockwise. See, this is another example. See, the big winding is the outer winding or the top winding, and this is the first winding and the bottom winding. You can tell when I push this the small winding inside the big winding, you can tell south is going to face north and south on top again. So in other words, everything is in the same direction. The flow of electrons are going to be, so the flow of electrons are going to be adding up. Each wire technically, or each winding is considered like a magnet. So each one, the closer it is, the more magnetism they get. And then I demonstrated like this here. You can tell if the magnets are like this, each one can be considered one layer or one winding. But if they're closer together, total magnetism will add up. But see, now I put these cardboards in between. They're a little bit far apart. So always the winding is supposed to be tight or close together. And then if I get an iron or any ferromagnetic here, because the charges are separated and they're extended all the way to the poles, it's not going to be effective here, or in other words here, it's not going to be really strong. But always the strength of the poles are on two poles. This is another experiment, and in fact, Andre Ampere was genius in electromagnetism. He discovered that the current flows through a wire twisted into a helix like a spring or corkscrew. The magnetic field is strengthened with each turn of wire. So what he discovered, if you have like four turns of wire compared to 10 or more, the more turns of wire you have, the more magnetism you have. Well, in fact, I came up with the Slinky Theory, and the reason why I came up with this theory, if you have a solenoid like this, or even if you have a straight wire like this, there is no way you can make or you can get any work out of this straight wire. It doesn't matter how much current flows in this wire. It doesn't make any difference. You will not be able to use that total magnetism. So what Andre Ampere did, he made a coil like this. So I came up with the Slinky Theory. That means that when the wire is bent like this, the flux line in this side is more compared to the other side. You can tell if I do it like this, it's exactly like a slinky. You can tell the flux lines are more, but the outside are less. Of course, this might be a little bit exaggeration, but like I said, this is a straight wire, but you can tell, even if I say each one, this concentric, flux lines are nanometer or even picometer apart. It might be exaggeration because I don't know, but this is just an estimate that, if I have concentric flux line around the wire, see what happened. This is my wire, but if I bend it, see what happened. See? The inside, the flux lines are getting much closer compared to the outside. You can tell. See? This is exactly like my Slinky Theory. Well, of course, there's another phenomenon called the slip. When we have a wire, it doesn't matter, copper, silver, aluminum, or lead, whatever the material, when we bend the wire, there's a phenomenon called the slip. Always the inner part or the inside the loop is a little bit more condensed compared to the outside. Well, of course, we cannot see it, it's microscopic. But I came up with this Slinky Theory. That means that, when we bend the wire, in other words, we recycle the total magnetism. That's exactly what Mr. Faraday and Ampere did. This is another example. So I just wanted to compare solenoids with magnets. You can tell when we have these magnets, see, it doesn't matter how many magnets you can put, 1,000 magnets in a row. See, always the charges are separated. And see how weak in the middle is? It's exactly the same on this one. See, regardless of the shape, always on the poles, we have more charges. But compared with this electromagnet, the results are exactly the same. You can tell on the poles we have more, or in other words, due to the separation of charges, we have more concentrated charges on the sides compared to the center. Now I'm going to connect this to 12 volt DC. You can tell. See how it's attracted strongly, but when you see here, the attraction is not that much. This is another one. See, I did exactly the same number of turns or winding, but this is 4-segmented solenoid. It's exactly like if I had like 4 magnets back to back like this, I separated, the charges are exactly the same. It doesn't matter how many winding, even if I have 1 turn of wire here, like that one over there, it's going to be exactly north and south, north and south. So this is exactly the same thing. So I'm going to connect this, you can tell. get there, see, you can tell north, you can tell south, north, south, north, south, north. In fact, Andre Ampere used a single loop in their formulas. A straight current carrying wire will not do any work, but when we form a loop or turn, the magnetic field is not scattered along the wire. It is confined inside the loop. My analogy, the loop recycles the magnetic field. It is like a hot gases exiting from the engine's exhaust. But when the turbocharger is added, the hot gases are recycled and add to the total efficiency of the engine. Well, another analogy is laser. A single passing photon can be recycled, reflected between two mirrors, and enhanced millions of times so that the result is laser coherent light. So you can tell, this is my analogy to Ampere. If we let the exhaust fumes go out, we won't have a good efficiency. But since it is recycled, and you can tell the efficiency go up. See, Ampere and Faraday both used a single loop. Amazingly, you can tell if you have a straight wire, it doesn't matter miles and miles and miles. It's not going to do any work. But as soon as you have a loop like this, you are recycling. So in other words, you're confining the entire magnetism. So if you have one loop, it's going to be less. Now another one, you add the total magnetism as long as the flow of current is in the same direction. So in other words, it's not changing. This is another experiment. What I did, this is just a sheet, so I rolled it to 2.5. You can tell almost like 8.5 inches are round, but this part is a square. But something special happened here. It's exactly like my wire when I connect it to 12 volt DC. It doesn't matter. I can rotate this 360 degrees. It doesn't make any difference. Always my side is going to be south and the opposite side is going to be north. But something special happened here, because see, these four corners are sharp. So I have exactly, instead of having two poles south and north, I have 8 distinct south, north, north, south. And it doesn't matter how I rotate this, always one side is going to be south and the other sharp corner is going to be north. And I will explain in a microscopic level, but now I'm going to show you this experiment first. See, when I connect this part is exactly like a thick wire, even though it's hollow, but it doesn't make any difference, you can tell. See? One side is south and the other side is north. But what happened here is exactly different. See, due to the sharp points here, the charges are separated. And in other words, there's a concentration of south and north, and each sharp corner is exactly the same tube, and this exactly the same current, same amount of electrons are flowing through. But what happened here, due to sharp points, we have more separation. So I'll show you. See, one side is always south and this corner is going to be north. And if I rotate it, it's exactly going to be like that. My logical analysis for the separation of charges when they encounter sharp points, one important factor is the separation of the charges is based on the cancellation and orientation of the dipoles, and finally the alignment with the electric field. You can tell this is exactly like my four corners or a square. You can tell the dipoles when they are subjected to electric field. See, one side is here, and that's as far as it can go, and then the others are just enhancing. But when it's round like this, like Earth, there is no way, or like my wire, there is no way. We don't have any sharp corners, but see, you can tell one side the concentrations of the dipoles are more. At the same time here in between, there's a cancellation. So the north-south, they cancel each other, but there's no way they can cancel it on the corner, because one or two, or it depends on how many or how sharp the corner is, always there will be concentration of dipoles. One side of the dipoles will facing the sharp corner, and the other side will be facing down. And the same thing here. So that's why we have distinct south-north, south-north, south-north. But when you compare to Earth, you can tell, or my round wires, you have only north and south, because the same thing happened here. Same thing happened here. The dipoles are canceling each other. I'm talking about trillions and trillions of dipoles. They cancel each other, and finally they settle here somewhere north and south. So this is my logical analysis for having 8 distinct poles instead of 2 when we have sharp corners. A sharp corner doesn't have to be exactly like this. It can be like knife, or it can be like, a little bit round, but on the side it's a little bit sharp, or it even can be a cut. If I have a sheet of conductor like this, if I cut it in between like a rectangle or a square, those are going to assume new polarities. This is another experiment. I used 4 inches thick rod, this aluminum rod. Well, what I did here, you can see, I cut the 4 corners. I made exactly like my previous experiment. See how sharp they are? So it doesn't matter which way the current is flowing. It's exactly like a wire. One side is going to be south, and the other side is going to be north. Even if I rotate this clockwise or counterclockwise, 360 degrees, the results are going to be the same. So my conclusion is, it doesn't matter if its current is flowing in a hollow tube like my previous experiment, or the solid like this, the separation of the charges are the same. So in other words, the interaction between the dipoles are exactly the same. Now I show exactly what I mean. See, when I connect this to 12 volt DC, you can tell it's exactly like a wire, but this one is 4 inches wire technically. You can tell it's always one side is south and the other side is north. Well, of course, if I change the flow of current to the other, this is going to be north and the other one is going to be south. But something amazing happened here. See, the current is flowing from here, from negative to positive. But what happened here, because these 4 corners are sharp, we have more concentrated charges. And like I explained, we have like south here, north here. If I rotate this again, you can tell we have the opposite side, we have north, south. So instead of having 2 distinct poles, south and north, we have 8 distinct poles. I'll show you. The north, south. If I rotate this, it's going to be exactly the same. This is also a block of aluminum. See how huge this block is. And it's like 13 by 3.5 by 1.5. It's exactly the same thing happened. When I have like flow of current from negative to positive, always this part is north, and see this part is going to be south due to the sharp corners. If I make this round, again we will have only 2. This is another experiment, but this time I used sheet of copper aluminum, but you can tell if you roll this, it's going to be exactly like a wire. But now I have 4 by 38, but if I connect this to 12 volt DC, this is exactly like a wire. So what happened, one side all the way is going to be south, and the other side. Hi, I have to repeat this question because I was low in a battery, and this is a sheet of copper and it doesn't matter how large. So what I did here, I cut this 4 by 30th, but you can see I made some holes, rectangle, round, square, and triangle. And even if I do like 10,000 holes, like in a micrometer, the charges are going to be separated. If I don't cut this rectangle in between, it's going to be south and north when I connect this to 12 volt DC. But as soon as I cut that rectangle or anything, or even a small holes, the charges will be separated. I show you. See, this is a neodymium magnet. It's a very strong magnet. So when I connect this to 12 volt DC, one side is going to be south all the way to that end, and the opposite side is going to be in. And it's exactly like a permanent magnet. If I hold this in between the poles, it's going to be extremely weak. So in other words, there won't be any interaction whatsoever. I'll show you. See, now I'm holding this neodymium magnet, which is north-south. You see, it's attracted. But if I put this over here, if I bring it over here, this is south, because I cut this rectangle, this part is going to be north. In other words, this is going to be independent like a magnet. I'll show you. See, it was attracted. This is another one, it's aluminum.